Right, guys, let's go over this. This problem is going to introduce us to one of the topics we're going to be talking today, which is about elimination regioselectivity. And you'll notice here that what we're doing is we're taking an alcohol and we're treating it with sulfuric acid. There's nothing else in that reaction. I've not indicated anything else in that reaction. There will be a solvent, but the solvent is not going to play a role mechanistically. It's not going to play a role. Right? So these are the conditions for alcohol dehydration. So, and this is really just the elimination of water. So mechanistically, what's going on, before we get into the three products, I think it's helpful to go through the mechanism, or at least what we would think the start of the mechanism would look like. So there really aren't too many things that can happen when you have strong acid and an alcohol other than just an acid-base reaction. So we're going to start out with protonating the alcohol. It's going to create a cationic water-leaving group, which will leave. Right? And so this is an electrophile or an intermediate with a leaving group that will form a tertiary carbocation when it leaves. Right? So it's okay to have that leave and form the tertiary carbocation. So if you're thinking about E1 versus E2, this is going to be a unimolecular elimination mechanism. All right, and we get to this common tertiary carbocation. Right, now when you look at this, whenever you do elimination, right, the proton that you're pulling has to have a specific relationship, spatial relationship, with the leaving group, or in this case, the carbocation. Right? And so when we were looking at E2 reactions the other day, we said that there has to be 3 bonds in between the proton that's being pulled and the leaving group that's being kicked out. Right? And so if we have a carbocation, that leaving group's already gone, right? Then we can say that there has to be 2 bonds in between the proton being pulled and the carbocation on the center. Right? So we have a couple of options here for which protons can be pulled. Right, we have 3 protons on this methyl group. I'll only just draw one of them in. Right, you can see that there's a 1-2 bond relationship between the actual proton and the carbocationic center. Right, we'll call this HA. On carbon in the ring to the left, we also have 2 protons on that carbon. Okay, and that has a 1-2 bond relationship with the carbocation center. Right, we'll call that HB. And then the carbon on the right, there's 1 hydrogen on that carbon. And we'll call that HC. Right, and again, if you count the number of bonds between the proton and the carbocation center, there are 2 bonds. Right, so the base that's going to interact with this molecule, it has 3 different options, and those 3 options are going to lead to 3 different products. Right, what would we use? What's a reasonable base for this mechanism?
I use the water.
The water that left here? I would say yeah, that's legal. maybe towards the end of the reaction, that's a better base. But what if this was like the very beginning of the reaction? We just set it up. What's probably the most probable base in the reaction?
Would it be the alcohol?
Good. Yeah, so we could use either water that we lost here. As long as we form water, right, in the mechanism before we use it, we can use it, right? If there's not water in the conditions, and then we're not forming water in the reaction, right, we can't suggest it as a base, right? So in this case, we're forming it, but if there's only one of these, there's going to be one molecule of water, right? At the beginning, we're going to have a lot of molecules of alcohol, right? So both are viable bases. One's a little more probable at the beginning, one's going to be a little more probable at the end. Okay. So just say HO, and then we'll put an R group. Right, and so the three mechanisms, pull proton A, will form the double bond on the methyl group outside, right? Pull proton B, and then we'll form a methyl group on the left side of the ring, right? And then if we pull proton C, we'll form a methyl group on the right side of the ring. Those are going to be our three options here. Right, of these three, product C is going to be the major product, right, especially if we let this cook for a while. Let's talk about why that is. First of all, does anybody have any questions on three products that are formed, mechanisms that we use to get there, dehydration reactions in general? Okay, so I will say whenever you're doing dehydration reactions, right, you want to avoid using solvents that can be nucleophilic, right? So if you're doing a dehydration, you don't want to use water as a solvent, right, because you're trying to get rid of water from the reactant. You typically don't want to use alcohols as solvents, right, because they can come in and act as nucleophiles as well. So usually we try to leave the nucleophilic solvents out of dehydration reactions. All right, let's look at alkenes. So we can, when we look at the stability or relative energy of different alkenes or alkenes that have different substituents on them, we can see a pretty clear trend. And that the stability is related to the number of substituents attached to that alkene. So if we look at this trend, the way that I drew this out, I didn't really give myself enough space, but the most stable alkene is going to be the tetrasubstituted alkene, right? The alkene with 4 different carbon groups coming off of it. Right, then we go to trisubstituted, right? And as we're losing a substituent, you can see the energy of these alkenes, the energy of these systems is increasing, right? So we have our trisubstituted. We have 3 different disubstituted alkenes, right? So we can get a trans disubstituted alkene, right? What we call a geminal disubstituted alkene. Those are going to be about the same energy, and then a cis disubstituted alkene, where the carbon groups are on the same side. Right? And then we have a monosubstituted alkene. So let's try to think about why we see this trend. Just like for a lot of other things when we're thinking about stability, it's good to think about the orbitals and the electron distribution. So we're going to be looking at these alkenes from the side view, right? So we'll make this into a trisubstituted alkene. There are going to be 2 methyl groups and 1 hydrogen. We'll make, say, this a hydrogen back here, right? And then we have other hydrogens on the methyl groups. Right, and then we'll make this one into a trans disubstituted alkene. And then let's draw some orbitals in there. So the orbital that is going to be important is going to be the pi star orbital, the carbon-carbon pi antibonding orbital. So what would that look like? How would we draw a pi antibonding orbital on the alkene? Yeah, so it kind of looks like the original p orbitals, right, that are trying to get apart from each other. Right, so when we draw the pi star, right, remember pi star is going to be the out of phase combination of the p orbitals. Pi star in both of them. Right, so when we're looking at these pictures, right, understanding, I tried to draw orbitals and bonds in a specific orientation or specific way. Why would it make sense that this would be more stable? The electrons in this system would be more stabilized than the electrons in this system. What's going on here that's not going on over there?
More emphasis on hyperconjugation.
Excellent. Yeah, so we have to look at hyperconjugation, just like we look at hyperconjugation for cation stability, right? We don't have an empty orbital, we don't have a low valent carbon, but we do have an empty orbital in the pi star orbital. And these sigma bonds, right, these are going to hydrogen, but they could really go to whatever atom is there, right? They can donate into those pi star orbitals. Okay, so there's going to be greater hyperconjugation. as you increase the substitution around that alkene, around that double bond. Right, and that's going to largely explain the thermodynamic stability of these alkenes. Now, when we get down to the di-substituted alkenes, right, we can rationalize that a trans alkene, just based on sterics, is going to be more stable than a cis alkene, right? Because here, those two methyl groups are on the same side, have to interact with each other. Trans alkene, those two methyl groups are on opposite sides, so they're experiencing the same amount of hyperconjugation, right? But there is a steric difference or a steric strain difference between these two. All right, questions about this? Okay, really important trend to note. This is going to come up again. And so when we're looking at this problem here, product that forms, you can see, is going to be the most thermodynamically stable product, right? The major product of this reaction. Right? And that's not to say that the others won't form, right? But they're just not going to form to the same quantity or to the same degree. So what this means for E1 chemistry anyway is that because these reactions are reversible, and we'll look at reactions where we're taking alkenes and adding acid and water and doing a hydration of that alkene. Right? And I'm sure you could rationalize the mechanism. Mechanism is just going to be the exact opposite of the mechanism that we just went over. So because these E1 reactions, these E1 dehydration reactions are reversible, right, they're going to be under thermodynamic control, which means like we can make one of the less stable products, but it's going to go back to the starting material, right? There's going to be some equilibrium where it goes back to the starting material, and eventually the most stable product is going to win out. And that's how we get to the major product. Contrast to this, E2 reactions are going to be under kinetic control. We don't think of them as being reversible. So let me give you an example. So first of all, we're going to just look at this really simple starting material. See if you can figure out the two products that would form through elimination, through E2 elimination. Don't worry about the reagents, right? Just consider that you're doing an E2 elimination, and there will be a base present in order to affect that. Actually, three products will form here. So who can give the IUPAC name of one of the products? Yes.
1-butene.
Excellent. 1-butene. All right, so that's one option. Yeah.
2-butene?
Okay, so there are going to be two different 2-butenes. Which one do you want?
I don't know.
E or Z?
E.
E. Okay. All right, so we're going to have two different isomers of 2-butene, right? So we'll have E2-butene. And we can also make Z2-butene. Okay, so those are the three options. Right? Of these, E2-butene is going to be the most substituted, or E and Z2-butene are the most substituted, right? But of those two, this is going to be the most stable, right? Lowest energy alkene. So if we treat this with, say, sodium ethoxide, and we carry this out in ethanol, and we heat it up, right, to promote elimination, what we're going to see is that the major product is going to be the E2-butene. If we change this up, right, still use an alkoxide base, but maybe make that base really big and bulky. And use the corresponding alcohol solvent, right? Apply some heat to promote elimination. The major product is going to be 1-butene. So what we're seeing here is that by changing the base, we're changing the regioselectivity of the reaction, right? We're still forming the same functional group, the alkene, we're just changing where it forms, right? The region on the molecule that it forms on. Okay? So because we can use a small base and make this the major product, right? Or change that to a large base and make that the major product, right? We can control the regioselectivity. Why this is or why this happens. Right, so the two mechanisms that we would see, right, ethoxide is going to pull mostly from the secondary carbon. Whereas the terpetoxide is going to pull mostly from the primary carbon. Both of these are still E2 mechanisms. You can see the relationship between the atom that's leaving and the proton that's being pulled. In E2 is a 3-bond relationship, right? And the atom that leaves takes the electrons in that bond with the atom.
Why would the ethyl group not just take off the same proton that the terpetoxide would?
Yeah, that's a good question. That's a good question. So, just like the alkenes have a difference in energy, the transition states that lead to those alkenes are also going to have a difference in energy. So the transition state is a combination, or it looks like the starting material and the product, right? So it's kind of halfway in between the starting material and the product. And so where that double bond forms is going to affect the stability of that transition state. So the more substituted transition state is going to be the lower energy transition state in this case, right? So when we're using a small base, what that means is that the small base, there's not going to be much difference in the interaction of the small base with this proton versus that proton, right? Kinetically speaking, right? It's going to be about as easy for this oxygen to pull this proton as it would be to pull that proton or approach the molecule, right? But the transition state that results so this double bond that is forming, right, the stability of that formation is really controlled by how many substituents are around it, right? So if the transition state is more substituted, then it's going to be a lower energy, more stable transition state, right? Once we get to a big base, though, now how these two molecules interact, there's going to be a difference, right? The small base, there's not going to be much difference in are they going to be able to approach each other. Right? This oxygen on ethoxide will be able to approach this proton just as easily as it will be able to approach that proton. Right? So the difference is really in the transition structure. With terpetoxide, because it's such a big, bulky base, it's going to be much harder for that terpetoxide to approach that proton, right? Much easier to approach that proton. So by increasing the steric bulk of the base, we can add that energy to the transition state, right? For the more substituted carbon. And so that's why kinetically we're forming the less substituted carbon more quickly. So let's draw this out in an energy diagram. Right, so let's consider, rather than looking at these two bases, let's consider terpetoxide pulling the primary proton versus terpetoxide pulling the tertiary proton. So here's our starting material. We'll have the primary on one side, or the monosubstituted alkene on one side, and the disubstituted alkene on the other side. Right, so we know that disubstituted alkene is going to be lower in energy overall thermodynamically. Right, the monosubstituted alkene is going to be higher in energy overall. And then we're using, for this reaction, we're going to be using the terpetoxide. Right, so we know it's a big, bulky base. Right, so these are E2 reactions, they happen in one step. How would we draw the transition states leading to these two products?
E2, so it's only going to be one step,
Good, yep.
which is the rate limiting step. And it should be a higher rate limiting step to go to the 1-butene.
So we're using the
Wait, no,
bulky
it's the other
base,
way.
this is the major product, right?
Right,
So that forms the most.
right.
So
I had
it
it
should-
the other way.
Good,
Because of the steric strainer and transition state, right?
good.
Big strainer.
Yeah, so when you think about the transition state here, you have secondary proton being pulled, and this is not very illustrative of how much those two things have to interact, right? But the transition state, major product, right, we're pulling the more available proton. Right, so lower energy transition state, since the E2 reaction is kinetically controlled, it's going to be the major product, right? But only if we're using that big bulk of this. Questions about this? Makes sense? Right. Okay, so next I want to talk about stereoselectivity or stereochemistry and elimination. Right, so if you look at the starting material we have, it's a chiral starting material, right? So we have two chiral centers. One chiral center has the leading group on it, and a hydrogen, and then the other chiral center is going to have a hydrogen and a deuterium. Right? And I'm putting the hydrogen and deuterium there just so we can track how this elimination has to take place from a stereochemical perspective. Right? So the two products that we would get are the two disubstituted alkenes that we would get. Be these two alkenes. Right? And so what this illustrates is that in order to make the trans alkene, we're pulling the proton, or sorry, the deuteron. In order to make the cis alkene, we're pulling the proton. Okay, and this really points to the conformation that these molecules have to adopt in order for E2 elimination to take place. so what this is ultimately illustrating is that for E2 elimination to take place, right, the proton and the leaving group have to have a very specific spatial relationship. Right? They have to have an antiperiplanar relationship where the dihedral angle has to be 180 degrees. There's a really good reason for that, and it has to do with orbitals. So I'm going to draw a sawhorse projection up here. We didn't do much with sawhorse projections, but they are useful occasionally. Here are my two chiral centers. Right? You can see that I've drawn this so that hydrogen here and the bromide leaving group have an antiperiplanar relationship, right? 180 degree dihedral. So the bromine's going straight up, the hydrogen is going straight down. Okay, so in order to get the carbon-bromine bond to break, in order to get the bromine to leave, what orbital do we have to interact with? Where do we have to put electrons? Think about substitution. We want a leaving group to leave. Where do the electrons have to go from the nucleophile? Yeah.
Would be the underside?
Yeah, the antibonding orbital, right? Carbon-bromine antibonding orbital. So there's our sigma star, carbon-bromine sigma star orbital. Right? And what set of electrons lines up perfectly with that sigma star orbital? Okay.
The hydrogen bond.
Great. Yeah, so this carbon-hydrogen sigma bonding orbital. And so this is the orbital basis for E2 elimination, and this is why the molecules have to adopt that specific conformation in order for the elimination, for that specific elimination to take place. Right? If we pull the proton, these electrons, which are making the pi bond, have to overlap with that sigma star orbital in order to kick out the bromine. Right? In order to do that, they have to have this antiperiplanar relationship. Okay. You can see when I pull the proton, right, or when the proton and the bromine have an antiperiplanar relationship, the two methyl groups are on the same side of that molecule. And so when we look at the product that would form from pulling the proton, right, two methyl groups are on the same side of the molecule. Okay. If we switch them around, this will be the last thing I draw out. If I switch this around, so I'm pulling the deuterium to make the bromine leave to get that elimination take place. Now the two methyl groups are on opposite sides of the molecule, right? The two methyl groups actually have an antiperiplanar relationship in this conformation. And so the product that would form would be the trans product where those two methyl groups are on opposite sides of the double bond. Right? So it's pretty easily, if we can get the molecule in the right conformation, right, to understand how it's undergoing E2 elimination, really easy to rationalize what the product is going to be, cis versus trans. Any questions about this? All right, we'll stop here. So we're a little bit behind. We've been going a little bit slower than I intended. Thinking about pushing the exam back a week to the February 15th. Does anybody object to that? If you do, and you just don't want to say it, let me know. But obviously there has to be a critical mass of people who object to it. Otherwise, it's going to be moved to the